NTFS is a proprietary file system developed by Microsoft. Starting with Windows NT 3.1, it is the default file system of Windows NT family. NTFS has several technical improvements over FAT and HPFS, the file systems that it superseded, such as improved support for metadata, and the use of advanced data structures to improve performance, reliability, and disk space utilization, plus additional extensions, such as security access control lists and file system journaling. History: in the mid-1980s, Microsoft and IBM formed a joint project to create the next generation of graphical operating system. The result of the project was OS/2, but Microsoft and IBM disagreed on many important issues and eventually separated. OS/2 remained an IBM project and Microsoft worked on Windows NT. The OS/2 file system HPFS contained several important new features. When Microsoft created their new operating system, they borrowed many of these concepts for NTFS. Probably as a result of this common ancestry, HPFS and NTFS share the same disk partition identification typecode. Sharing an ID is unusual, since there were dozens of available codes, and other major file systems have their own code. FAT has more than 9. Algorithms identifying the file system in a partition type 07 must perform additional checks. Developers: NTFS developers include Tom Miller, Gary Kimura, Brian Andrew, David Gerbel. Versions: Microsoft has released 5 versions of NTFS, v1.0 released with Windows NT 3.1 in 1993. v1.0 is incompatible with v1.1 and newer. Volumes written by Windows NT 3.5x cannot be read by Windows NT 3.1 until an update is installed. v1.1 released with Windows NT 3.5, in fall 1994, v1.2 released with Windows NT 3.51 in 1995. Supports compressed files, named streams and access control lists, v3.0 released with Windows 2000. Supports disk quotas, encrypting file system, sparse files, reparse points, update sequence number journaling, the $extend folder and its files. Reorganize security descriptors so that multiple files using the same security setting can share the same descriptor. v3.1 released with Windows XP in autumn 2001. Expanded the master file table entries with redundant MFT record number. The NTFS's version number should not be confused with the NTFS format version number. Windows Vista implemented Transactional Ntfs, NTFS symbolic links, partition shrinking and self-healing. All except NTFS symbolic links are operating systems features. Windows Vista also introduced persistent shadow copies for use with System Restore on previous versions features. Persistent shadow copies, however, are deleted when the older operating system mounts that NTFS volume. This happens because the older operating system does not understand the newer format of persistent shadow copies. Features: NTFS v3.0 includes several new features over its predecessors: sparse file support, disk usage quotas, reparse points, distributed link tracking, and file-level encryption, also known as the encrypting file system. Scalability: in theory, the maximum NTFS volume size is 264 clusters. However, the maximum NTFS volume size as implemented in Windows XP Professional is 232 clusters, partly due to partition table limitations. For example, using 64 kilobytes clusters, the maximum Windows XP NTFS volume size is 256 TBs minus 64 KBs. Using the default cluster size of 4 kilobytes, the maximum NTFS volume size is 16 terabytes minus 4 kilobytes. Because partition tables on master boot record disks only support partition sizes up to 2 terabytes, dynamic or GPT volumes must be used to create NTFS volumes over 2 terabytes. Booting from a GPT volume to a Windows environment requires a system with UEFI and 64-bit support. The maximum theoretical file size on NTFS is 16 OEB-1 kilobyte or 1844674407370955059 bytes. With Windows 8 and Windows Server 2012, the maximum file size implemented is 256 terabytes 64 kilobytes or 281,474,976,645,120 bytes. NTFS supports a maximum cluster size of 64 kilobytes. Journaling. NTFS is a journaling file system and uses the NTFS log to record metadata changes to the volume. It is a critical functionality of NTFS for ensuring that its internal complex data structures, or data moves performed by the defragmentation API, the modifications to MFT records, and indices will remain consistent in case of system crashes, and allow easy rollback of uncommitted changes to these critical data structures when the volume is remounted. The Usn Journal is a system management feature that records changes to files, streams and directories on the volume, as well as their various attributes and security settings. The journal is made available for applications to track changes to the volume. This journal can be enabled or disabled on non-system volumes and is not enabled by default for a newly added drive. Hard links. Hard links allows different file names to refer to the same file contents. Hard links are similar to directory junctions, but refer to files instead. Hard links may link to files in the same volume only because each volume has its own MFT. Hard links have their own file metadata, so a change in file size or attributes under one hard link may not update the others until they are opened. Hard links were originally included to support the POSIX subsystem in Windows NT. Windows uses hard links to support short file names in NTFS. Operating system support is needed because there are legacy applications that can work only with 8.3 file names. In this case, an additional file name record and directory entry is added, but both 8.3 and long file name are linked and updated together, unlike a regular hard link. Alternate data streams. Alternate data streams allow more than one data stream to be associated with a file name, using the format file name, stream name. NTFS streams were introduced in Windows NT 3.1, to enable services for Macintosh to store resource forks. Although current versions of Windows Server no longer include SFM, third-party Apple filing protocol products still use this feature of the file system. Very small ADS are added by Internet Explorer and recently by other browsers to mark files downloaded from external sites as possibly unsafe to run. The local shell would then require user confirmation before opening them. When the user indicates that they no longer want this confirmation dialog, this ADS is deleted. Alternate streams are not listed in Windows Explorer, and their size is not included in the file size. Only the first stream is preserved when a file is copied to a FAT formatted USB drive, is attached to an email, or is uploaded to a website, so using alternate streams for critical data may cause problems. Microsoft provides a tool called Streams to view streams on a selected volume. Starting with Windows PowerShell 3.0, it is possible to manage ADS natively with 7 commandlets: add content, clear content, get item, out string, remove item, set content. Malware has used alternate data streams to hide code. As a result, malware scanners and other special tools now check for alternate data streams. File compression. NTFS can compress files using Usn Nt1 algorithm. Files are compressed in 16 cluster chunks. With 4 KB clusters, files are compressed in 64 KB chunks. The compression algorithms in NTFS are designed to support cluster sizes of up to 4 kilobytes. When the cluster size is greater than 4 kilobytes in an NTFS volume, NTFS compression is not available. If the compression reduces 64 KB of data to 60 KB or less, NTFS treats the unneeded 4 KB pages like empty sparse file clusters so they are not written. This allows for reasonable random access times as the OS just has to follow the chain of fragments. However, large compressible files become highly fragmented since every chunk less than 64 kilobytes becomes a fragment. Single-user systems with limited hard disk space can benefit from NTFS compression for small files, from 4 KB to 64 KB or more, depending on compressibility. Files less than 900 bytes or so are stored within the directory entry at the MFT. Flash memory, such as SSD drives, do not have the head movement delays of hard disk drives, so fragmentation has only small effects. Users of fast multi-core processors will find improvements in application speed by compressing their applications and data, as well as a reduction in space used. Note that SSDs with Ntfs controllers already compress data. However, since less data is transferred, there is a reduction in IOs. The best use of compression is for files that are repetitive, seldom written, usually accessed sequentially, and not themselves compressed. Log files are an ideal example. Compressing system files needed at boot time, like drivers, NTLDR, WinLoadX, or bootmg, may prevent the system from booting correctly, as compression filters are not available then. However, in later editions of Windows, compression of important system files is disallowed. Files may be compressed or decompressed individually for a drive, directory, or directory tree, becoming a default for the files inside. Although read-write access to compressed files is mostly transparent, Microsoft recommends avoiding compression on server systems and/or network shares holding roaming profiles because it puts a considerable load on the processor. Compression is not recommended by Microsoft for files exceeding 30 MB because of the performance hit. Since many fragments are created for compressible files, defragmentation may take longer. Sparse files. Sparse files are files interspersed with empty segments for which no actual storage space is used. To the applications, the file looks like an ordinary file with empty regions seen as regions filled with zeros. Database applications, for instance, may use sparse files. As with compressed files, the actual sizes of sparse files are not taken into account when determining quota limits. Volume shadow copy. The Volume Shadow Copy service keeps historical versions of files and folders on NTFS volumes by copying old, newly overwritten data to shadow copy via copy-on-write technique. The user may later request an earlier version to be recovered. This also allows data backup programs to archive files currently in use by the file system. On heavily loaded systems, Microsoft recommends setting up a shadow copy volume on a separate disk. Transactions. As of Windows Vista, applications can use Transactional Ntfs to group changes to files together into a transaction. The transaction will guarantee that all changes happen, or none of them do, and it will guarantee that applications outside the transaction will not see the changes until they are committed. It uses similar techniques as those used for volume shadow copies to ensure that overwritten data can be safely rolled back, and a CLFS log to mark the transactions that have still not been committed, or those that have been committed but still not fully applied. Transactional Ntfs does not restrict transactions to just the local Ntfs volume, but also includes other transactional data or operations in other locations such as data stored in separate volumes, the local registry, or SQL databases, or the current states of system services or remote services. These transactions are coordinated network-wide with all participants using a specific service, the DTC, to ensure that all participants will receive same commit state, and to transport the changes that have been validated by any participant. Transactional Ntfs allows, for example, the creation of network-wide consistent distributed file systems, including with their local live or offline caches. Encryption. Encrypting file system provides strong and user-transparent encryption of any file or folder on an NTFS volume. EFS works in conjunction with the EFS service, Microsoft's Crypto API and the EFS file system runtime library. EFS works by encrypting a file with a bulk symmetric key, which is used because it takes a relatively small amount of time to encrypt and decrypt large amounts of data than if an asymmetric key cipher is used. the symmetric key that is used to encrypt the file is then encrypted with a public key that is associated with the user who encrypted the file, and this encrypted data is stored in an alternate data stream of the encrypted file. To decrypt the file system uses the private key of the user to decrypt the symmetric key that is stored in the file header. It then uses the symmetric key to decrypt the file. Because this is done at the file system level, it is transparent to the user. Also, in case of a user losing access to their key, support for additional decryption keys has been built into the EFS system, so that a recovery agent can still access the files if needed. NTFS provided encryption and NTFS provided compression are mutually exclusive. However, NTFS can be used for one and a third-party tool for the other. The support of EFS is not available in Basic, Home and Media Center versions of Windows, and must be activated after installation of Professional, Ultimate and Server versions of Windows or by using enterprise deployment tools within Windows domains. Quotas. Disk quotas were introduced in NTFS v3. They allow the administrator of a computer that runs a version of Windows that supports NTFS to set a threshold of disk space that users may use. It also allows administrators to keep track of how much disk space each user is using. An administrator may specify a certain level of disk space that a user may use before they receive a warning, and then deny access to the user once they hit their upper limit of space. Disk quotas do not take into account NTFS's transparent file compression, should this be enabled. Applications that query the amount of free space will also see the amount of free space left to the user who has a quota applied to them. Reparse points. NTFS reparse points, introduced in NTFS v3, are used by associating a reparse tag in the user space attribute of a file or directory. When the object manager parses a file system name lookup and encounters a reparse attribute, it will reparse the name lookup, passing the user-controlled reparse data to every file system filter driver that is loaded into Windows. Each filter driver examines the reparse data to see whether it is associated with that reparse point, and if that filter driver determines a match, then it intercepts the file system call and executes its special functionality. Reparse points are used to implement volume mount points, directory junctions, hierarchical storage management, native structured storage, single-instance storage, and symbolic links. Resizing. Starting with Windows Vista, Microsoft added the built-in ability to shrink or expand a partition, but this capability is limited because it will not relocate page file fragments or files that have been marked as unmovable. So shrinking will often require relocating or disabling any page file, the index of Windows search, and any shadow copy used by System Restore. Various third-party tools are capable of resizing NTFS partitions. Internals. Internally, NTFS uses B+ trees to index file system data. Although complex to implement, this allows faster file lookup times in most cases. A file system journal is used to guarantee the integrity of the file system metadata but not individual files' content. Systems using NTFS are known to have improved reliability compared to FAT file systems. NTFS allows any sequence of 16-bit values for name encoding except 0x0000. This means UTF-16 code points are supported, but the file system does not check whether a sequence is valid UTF-16. File names are limited to 255 UTF-16 code points. Certain names are reserved in the volume root directory and cannot be used for files. These are $MFT, $mftmyer, $logfile, $volume, $atf, $bitmap, $boot, $badclass, $secure, $erfcars, and $extend and $extend are both directories. The others are files. The NT kernel limits full paths to 32,767 UTF-16 code points. There are some additional restrictions on code points and file names. Master file table, in NTFS, all file, directory and metafile data file name, creation date, access permissions, and size are stored as metadata in the master file table. This abstract approach allowed easy addition of file system features during Windows NT's development. An interesting example is the addition of fields for indexing used by the Active Directory software. This also enables software like Everything or UltraZitch to perform instantaneous real-time searches for file and folder names, without relying on an indexing service. The MFT structure supports algorithms which minimize disk fragmentation. A directory entry consists of a file name and a file ID, which is the record number representing the file in the master file table. The file ID also contains a reuse count to detect stale references. While this strongly resembles the WFID of files 11, other NTFS structures radically differ. Metafiles. NTFS contains several files that define and organize the file system. In all respects, most of these files are structured like any other user file, but are not of direct interest to file system clients. These metafiles define files, back up critical file system data, buffer file system changes, manage free space allocation, satisfy BIOS expectations, track bad allocation units, and store security and disk space usage information. All content is in an unnamed data stream, unless otherwise indicated. These metafiles are treated specially by Windows and are difficult to directly view. Special purpose-built tools are needed. One such tool is the NFIX that is freely distributed as part of the Microsoft OEM support tools. For example, to obtain information on the $MFT master file table segment, the following command is used: nfixc $MFT, attribute lists, attributes, and streams. For each file described in the MFT record, there's a linear repository of stream descriptors, packed together in a variable length record, with extra padding to fill the fixed 1 KB size of every MFT record, and that fully describes the effective streams associated with that file. Each stream itself is a single type or file create API call, a single optional stream name, plus optional associated data for that stream. For NTFS, the standard data of files, or the index data for directories, are handled the same way as other data for alternate data streams, or for standard attributes. They are just one of the attributes stored in one or several attribute lists. For each file described in the MFT record, the stream descriptors identified by there must be unique. Additionally, NTFS has some ordering constraints for these descriptors. There's a predefined null stream type, used to indicate the end of the list of stream descriptors in the streams repository for that file. It must be present as the last stream descriptor in each stream repository. Some stream types are required and must be present in each MFT record, except unused records that are just indicated by a stream with null stream type. This is the case for the standard attributes that are stored as a fixed size record and containing the timestamps and other basic single-bit attributes. Some stream types cannot have a name and must remain anonymous. This is the case for the standard attributes, or for the preferred NTFS file name stream type, or the short file name stream type, when it is also present. It is also possible for a file to only contain a short file name, in which case it will be the preferred one, as listed in the Windows Explorer. The file name streams stored in the streams repository do not make the file immediately accessible through the hierarchical file system. In fact, all the file names must be indexed separately in at least one separate directory on the same volume, with its own MFT entry and its own security descriptors and attributes, that will reference the MFT entry number for that file. This allows the same file or directory to be hard-linked several times from several containers on the same volume, possibly with distinct file names. The default data stream of a regular file is a stream of type $data but with an anonymous name, and the ADSs are similar but must be named. On the opposite, the default data stream of directories has a distinct type, but are not anonymous. They have a stream name that reflects its indexing format. All streams of a given file may be displayed by using the NFIX that is freely distributed as part of the Microsoft OEM support tools. Windows system calls may handle alternate data streams. Depending on the operating system, utility and remote file system, a file transfer might silently strip data streams. A safe way of copying or moving files is to use the backup read and backup write system calls, which allow programs to enumerate streams, to verify whether each stream should be written to the destination volume and to knowingly skip unwanted streams. Resident versus non-resident data streams. To optimize the storage and reduce the I/O overhead for the very common case of streams with very small associated data, NTFS prefers to place this data within the stream descriptor, instead of using the MFT entry space to list clusters containing the data. In that case, the stream descriptor will not store the data directly but will just store an allocation map pointing to the actual data stored elsewhere on the volume. When the stream data can be accessed directly from within the stream descriptor, it is called resident data by computer forensics workers. The amount of data that fits is highly dependent on the file's characteristics, but 700 to 800 bytes is common in single-stream files with non-lengthy file names and no ACLs. Some stream descriptors cannot be made non-resident. Encrypted by NTFS, sparse data streams, or compressed data streams cannot be made resident. The format of the allocation map for non-resident streams depends on its capability of supporting sparse data storage. In the current implementation of NTFS, once a non-resident stream data has been marked and converted as sparse, it cannot be changed back to non-sparse data, so it cannot become resident again, unless this data is fully truncated, discarding the sparse allocation map completely. When a non-resident data stream is too much fragmented, so that its effective allocation map cannot fit entirely within the MFT record, the allocation map may be also stored as a non-resident stream, with just a small resident stream containing the indirect allocation map to the effective non-resident allocation map of the non-resident data stream. When there are too many streams for a file, so that their descriptors cannot fit all within the MFT record, a non-resident stream may also be used to store an additional repository for the other stream descriptors, using the same format as the one used in the MFT record, but without the space constraints of the MFT record. The NTFS file system driver will sometimes attempt to relocate the data of some of these non-resident streams into the stream's repository, and will also attempt to relocate the stream descriptors stored in a non-resident repository back to the stream repository of the MFT record, based on priority and preferred ordering rules, and size constraints. Since resident files do not directly occupy clusters, it is possible for an NTFS volume to contain more files on a volume than there are clusters. For example, a 74.5 GB partition NTFS formats with 19,543,064 clusters of 4 KB. Subtracting system files leaves 19,526,158 clusters free for files and indices. Since there are 4 MFT records per cluster, this volume theoretically could hold almost 4 19,526,158 equals 78,104,632 resident files. Opportunistic locks. Opportunistic locks allow clients to alter their buffering strategy for a given file or stream in order to increase performance and reduce network use. Op locks apply to the given open stream of a file and do not affect op locks on a different stream. Op locks can be used to transparently access files in the background. A network client may avoid writing information into a file on a remote server if no other process is accessing the data, or it may buffer read-ahead data if no other process is writing data. Windows supports 4 different types of op locks: Level 2 op lock, multiple readers, no writers. Level 1 op lock, exclusive access with arbitrary buffering. Batch op lock, a stream is opened on the server, but closed on the client machine. Filter op lock, applications and file system filters can back out when others try to access the same stream. Opportunistic locks have been enhanced in Windows 7 and Windows Server 2008-02 with per-client op lock keys. Time. Windows NT and its descendants keep internal timestamps as UTC and make the appropriate conversions for display purposes. Therefore, NTFS timestamps are in UTC. For historical reasons, the versions of Windows that do not support NTFS all keep time internally as local zone time, and therefore so do all file systems other than NTFS that are supported by current versions of Windows. This means that when files are copied or moved between NTFS and non-NTFS partitions, the OS needs to convert timestamps on the fly. But if some files are moved when daylight saving time is in effect, and other files are moved when standard time is in effect, there can be some ambiguities in the conversions. As a result, especially shortly after one of the days on which local zone time changes, users may observe that some files have timestamps that are incorrect by 1 hour. Due to the differences in implementation of DST in different jurisdictions, this can result in a potential timestamp error of up to 4 hours in any given 12 months. Interoperability. While the different NTFS versions are for the most part fully forward and backward compatible, there are technical considerations for mounting newer NTFS volumes in older versions of Microsoft Windows. This affects dual booting, and external portable hard drives. For example, attempting to use an NTFS partition with previous versions on an operating system that does not support it will result in the contents of those previous versions being lost. A Windows command line utility called convertx can convert supporting file systems to NTFS, including HPFS, FAT16 and FAT32. Mac OS X 10.3 and later include read-only support for NTFS formatted partitions. The GPL-licensed NTFS 3G also works on Mac OS X through Fuse and allows reading and writing to NTFS partitions. A performance-enhanced commercial version, called Tuxera NTFS for Mac, is also available from the NTFS 3G developers. Paragon Software Group sells a read-write driver named NTFS for Mac OS X, which is also included on some models of Seagate hard drives. Native NTFS write support has been discovered in Mac OS X 10.6 and later, but is not activated by default, although workarounds do exist to enable the functionality. However, user reports indicate the functionality is unstable and tends to cause kernel panics, probably the reason why write support has not been enabled or advertised. Linux kernel versions 2.2.0 and later include the ability to read NTFS partitions. Kernel versions 2.6.0 and later contain a driver written by Anton Altoparmakov and Richard Russin which supports file read, overwrite and resize. 3 user space drivers exist for NTFS support. They are built on the file system and user space, a Linux kernel module tasked with bridging user space and kernel code to save and retrieve data. All 3 are licensed under the terms of the GNU General Public License. Due to the complexity of internal NTFS structures, both the built-in February 6.14 kernel driver and the Fuse drivers disallow changes to the volume that are considered unsafe, to avoid corruption. 2 proprietary solutions also exist, Tuxera NTFS, a high-performance read-write commercial kernel driver, mainly targeted for embedded devices from Tuxera, which also develops NTFS 3G. NTFS for Linux, a commercial driver with full read-write support from Paragon Software Group. Ecom Station and FreeBSD offer read-only NTFS support. A free third-party tool for BOS, which was based on NTFS 3G, allows full NTFS read and write. NTFS 3G also works on Mac OS X, FreeBSD, NetBSD, Solaris, QNX and Haiku, in addition to Linux, through Fuse. A free for personal use read-write driver for MS-DOS called NTFS for DOS also exists. Ahead Software developed a NTFS READ driver for Drive DOS 7.0x between 2002 and 2004. It was part of their Nero Burning Room software. OpenBSD offer native read-only NTFS support by default on i386 and UNT64 platforms as of version 4.9 released May 1, 2011. Read-write support through NTFS 3G are possible in OpenBSD current as of November 1, 2013 as OpenBSD now has its own Fuse implementation and NTFS 3G are available from ports. See also, Comparison of file systems. NTFS DOS, NTFS RESIZE, references. Further reading. External links. Microsoft, NTFS Technical Reference, Microsoft, FSUtil File, LSOFT Technologies, ntfs.com.